Welcome, my dear students. This is our second class under Haloalkanes and Haloarenes. Last class we studied how to name IUPAC name nomenclature, then common names, all those things we studied. Today we are going to study how to prepare haloalkanes, especially monohaloalkane, right? So this is very important because today lot of things we are going to learn. For example, mechanisms. Some you can remember Markovnikov's rule you studied in 11th class, right? Anti-Markovnikov rules. Then some basic mechanisms also we will going to study. So now let's start. So first thing, how we will prepare monohaloalkane from alcohols. So starting material is alcohol. So from that, how we will synthesize monohaloalkane means Rx. ROH is given. From ROH we are going to synthesize Rx. Correct? This is our target. We have alcohol, we have to convert that into halo compound. This is the simple target. Now, what is X? Here X can be fluorine, chlorine, bromine, iodine. But here the most important point is, generally we don't use fluorine here. Why? Because generally this fluorine and this hydrogen and X, this bond, step by step we are going to learn. From this ROH we are going to get Rx. So for that actually we need to use HX. Now HX means HF, HCl, HBr, HI. So out of these four, fluorine generally we don't use this technique to prepare RF, because this HF bond is very strong and it is very difficult to break that. So that's why it is not that much common. And iodine, here also we have some problem, we will discuss after some time. But mostly whatever we are going to discuss, that all those common preparation methods mainly for Cl and Br, means we will use HCl and we will use HBr. Mostly we will focus on these two things, right? So here you can see from ROH, and here we are writing HX in presence of ZnCl2. Now what product we will get here? Now just check. This ZnCl2 is used to break this RO bond. R means it can be methyl, ethyl, propyl, butyl, or any alkyl group, right? It can be 1 degree, 2 degree, 3 degree, anything. So basically this carbon oxygen bond, it is strong bond, relatively strong bond. To break this bond we use ZnCl2. Now you just think in this way. We have HX. HX means it is related, acid. It is just like acid, right? HF, HCl, HBr, HI, these are all acids, means it can easily lose H+. So ROH, if HX we are using, so basically in presence of HX we will get OH2+, because HX is donating H+ plus X-, right? This H+ will be used to protonate OH. Next step, this X- is there. So this X- will attack this carbon and this OH2 will be released. So that's mean you are going to get Rx, right? You are going to get Rx plus water. Clear na? Water is coming from OH2 and this is the mechanism. So what is the role of ZnCl2? To weaken this RO bond, to weaken this R oxygen bond, means carbon oxygen bond. Correct? This is the way. So here we have one example. Here we have ethyl and OH, ethyl alcohol. In presence of HCl and ZnCl2, what we are going to get? So this H+, so H+ will be added here, means basically you will get OH2+, and then this Cl- will attack this carbon and water will be released. So basically you will get ethyl chloride plus water. Okay, easy mechanism. This is very easy. Now just check this process. this process actually it is following one intermediate, carbocation intermediate. So actually see, when OH2 we have, so from that, so let me write in a clear way, step by step, then it will be much more clear to you. Just check, ROH we have, and we are adding HX, so we will get ROH2 plus, then this will be released and you will get R plus, which is carbocation, right? Which is carbocation. And now this carbocation will be attacked by X minus. So X minus already is there, na? So here plus X minus. So this X minus will attack this and you will get Rx. So basically, whenever we have opportunity to generate carbocation, there is a high chance that rearrangement will be happening, right? So always you have to check, whenever if there is any possibility, एक थोड़ा सा भी possibility हो that there is a chance of rearrangement, you have to focus on that. Now if you consider one example, so in this case there is no chance of rearrangement, because this is 1 degree carbocation. 3 degree carbocation is more stable than 2 degree than 1 degree. Clear? Why? Because 3 degree carbocation means 3 other methyl group or alkyl groups are there which are stabilizing this carbocation. Like in normal way, this carbocation is more stable than this, correct? So 3 degree carbocation, instead of it is becoming jumble. This carbocation is more stable than, say, this, then this, means other will be hydrogen. Okay, 1, 2, 3, 4. So 3 degree carbocation will be more stable than 2 degree, and that will be more stable than 1 degree. So that's mean if there is any chance of getting rearrangement, then you have to focus on that. So this is all. This is about addition of HX. Now here we have these 3 methods: 1 degree alcohol, and by the way, this concentrated HCl and ZnCl2, this is called Lucas reagent. So whenever we have this reagent, concentrated HCl, hydrochloric acid, and ZnCl2, this means Lucas reagent. In question paper, maybe they will give direct name Lucas reagent instead of giving concentrated HCl and ZnCl2, or they can directly give this concentrated HCl and ZnCl2. So if we have 1 degree, if we have 2 degree, and if we have 3 degree alcohols, and we are adding Lucas reagent, what will be the product? Means what will be the product means basically what will be your observation. We are focusing on that observation, means how we will distinguish 1 degree alcohol, 2 degree alcohol, and 3 degree alcohols among them. Okay, focus is how we will distinguish them. So just you tell me, whenever we have 1 degree alcohol, just focus this. 1 degree alcohol means this one, CH3 bond CH2. So after removing this OH2, you will get this carbocation, correct? This is 1 degree carbocation. Now CH3 bond CH, and here let's consider CH3 plus, okay, 1, 2, 3, 4. So this is 2 degree, and CH3 bond C, CH3 and CH3, and here positive. So here we have 1 degree, here we have 2 degree, and here we have 3 degree. Now you tell me which carbocation is most stable. Obviously 3 degree carbocation, right? So that's mean whenever we have 3 degree alcohol, that will react very fast in presence of Lucas reagent. Means water will be released, like already I showed that mechanism, that this from ROH, OH will become OH2 and water will be released and positive charge will be on the alkyl part. Now if this alkyl part is 3 degree, very stable. So that means this reaction will be very fast. If this carbocation is 1 degree, which is not that much stable, so that means reaction will be very slow, right? Reaction will be very slow in case of 1 degree carbocation. So that's mean the conclusion is we have 1 degree alcohol, 2 degree alcohol, 3 degree alcohol. If we add Lucas reagent, very fast reaction will be happening in case of 3 degree alcohol, means immediately in second you will get product. In second means immediately you will get product. Now if we have 1 degree alcohol, so here basically 1 degree alcohol means it is giving 1 degree carbocation, which is not that much stable, means reaction will not try to move forward. So here reaction will be very slow, very slow, or you can say there will be almost no reaction, right? There will be almost no reaction. And 2 degree alcohol means, yes, here reaction will be happening, but reaction will take some time, maybe 5 minutes, right? So here, so this turbidity means this represents product. Alkyl halide, I said na, alkyl halide will be your product. So here 1 degree alkyl halide, 2 degree alkyl halide, and 3 degree alkyl halide, correct? So alkyl halide means that will give turbidity. Now in case of 1 degree alcohol, since reaction is not happening, that's why almost no turbidity. In case of 2 degree alcohol, yes, reaction is happening, but it is slow. It will take, by 5 minutes you will get turbidity. Next, in case of 3 degree alcohol, immediate reaction you will get. So you will get immediate turbidity. So this is the way, based on Lucas reagent, you can distinguish 1 degree alcohol, 2 degree alcohol, and 3 degree alcohol. I hope this is clear. This is the addition of HX, or how you are getting alkyl halide from alcohol. Now next part, here we have these two questions. Remember last slide we discussed, if carbocation is there and there is any chance of going towards rearrangement, if there is any chance of rearrangement, then it will be happening. So just check this, how we will identify product. So if you write this product, so here we have CH, and here we have CH3, and here also one CH3, correct? Here we have CH, and here CH3, and here OH. This is the structure. Now we are adding HCl. So what you will get? First, this H plus will be added here, right? So what you will get? CH3 bond CH, here CH3, next CH, CH3, and here OH2 plus, correct? OH2 plus. After this, if you remove this part, then this carbon will get positive charge, right? And you are getting carbocation. You are getting carbocation, correct? You are getting carbocation. Now you tell me, this carbocation is having which degree? This carbocation is connected to two other carbons, so that's why this is 2 degree, correct? This is 2 degree. Now, is there any chance of getting 3 degree carbocation? Let's see. So here hydrogen we have. Instead of writing that hydrogen, I am writing this hydrogen. Here. Okay. Now, if this hydrogen as H minus shift here, H minus means hydride, not H plus, hydride, as H minus, if it shifts from this carbon to the next carbon, means 1 to shift, then what you will get? You will get CH3, then carbon here CH3, here positive charge, bond C, H2, CH3, correct? We will get this one. So that's mean here what is the degree here? 3 degree. Always I said 3 degree carbocation is more stable than 2 degree and then 1 degree. So here this reaction has opportunity to convert 2 degree carbocation into 3 degree. So that's why here 1 to hydride H minus shift is happening, and here carbocation is there. Next step, what will happen? Cl minus already H plus is used, and Cl minus will attack this carbocation, and what product you will get? CH3, CH3, and here Cl will be added, CH2, CH3. So this is our product. So in this case, we have observed that hydride shift is happening in this example. Now second example, can you try the second example? Can you try the second example? What will be the product in this case? So let's draw this. Carbon, we have 3-methyl, next we have carbon, here hydrogen, there CH3 and OH. This is the structure, correct? Now HCl we are adding, so acid, so OH2 plus, and it will be released, and you will get positive charge on this carbon. You will get positive charge on this carbon. Now what is the degree of this carbon? So here the degree is 1 carbon, 2 carbon. This carbocation is attached to 2 other carbons, so that means 2 degree. So this carbon is 2 degree. Now is there any chance of converting this 2 degree into 3 degree? Yes. Just we have methyl, na? Methyl shift will happen here. So after this, what you will observe? CH3 bond C, positive charge will be here. CH3 bond C, CH3 and CH3, and here hydrogen. Correct? So now here, what is the degree? 3 degree. Next, again we have Cl minus in the medium, right? We have Cl minus in the medium. So Cl minus will attack this carbon. And what will be your final product? CH3, C, CH3, and here Cl we have bond CH, CH3 whole 2. So this will be our product. So in this case, so first example we observed 1,2 hydride shift. Second example we observed 1,2 methyl shift. So these two are very, very important example, right? I hope this is clear. Next part, this one, can you guess the product? So here basically, first case, again alcohol we have, and we have KBr and H2SO4. Now just check, KBr is there, so that's mean we are going to prepare alkyl bromide. Last example we studied alkyl chloride. Now how to prepare alkyl bromide, this is the process. And next one is alkyl iodide. We will learn these two things. So here we have KBr and H2SO4. If they react together, what you will get? You will generate HBr. Basically you need HX. Somehow you need HX. Now how we will form HX in the medium? If you add KBr and H2SO4 together, you will get HBr. Or else you have to directly add HBr. Either you add directly, HBr, or instead of HBr, you can add KBr and H2SO4. So they will together, they will mix, they will react and produce HBr, and that HBr will react with ROH, and you will get what product? RX, means RBr in this case, correct? RBr, and you are getting KHSO4 and H2O as byproduct. So now say here we have the same story, KBr and H2SO4 reacting, and you are giving HBr, just exchange of hydrogen. Next step, ROH, like previous one, HBr and ROH is reacting, and you are getting direct substituted product RBr, and then H2O, that is the byproduct. So if you add these two things, if you add these two reaction, so you will get ROH plus KBr plus H2SO4. This should be here, RBr plus H2SO4 plus KHSO4. Okay, so this is our entire reaction. So idea is same, to convert alcohol into alkyl halide or specially alkyl bromide, you need HBr. Now how you will get HBr? Either you directly add HBr or you add KBr and H2SO4. So KBr and H2SO4, they will react and produce HBr, and automatically in the reaction medium HBr is generating, and that HBr will be reacting with alcohol. So this is the method. Next, now you just check here KBr and H2SO4 we are using, but here instead of H2SO4 we are adding H2PO4. Why? We can directly use H2SO4, means we can replicate this previous reaction, but यहाँ पे हम लोग H3PO4 use कर रहे हैं. Why? Reason is that, see this Ki and this H, if you consider H2SO4, H2SO4 is H2SO4 is strong reducing agent, sorry, strong oxidizing agent, strong oxidizing agent. So if it is very strong oxidizing agent, if in the medium I minus is present like Ki, it will convert that into I2. It will oxidize iodide into iodine. For this reaction we need Hi. We need Hi. But in the reaction medium, if I2 is produced, you will not get your desired reaction, correct? जो हम लोगों को चाहिए वो तो नहीं मिलेगा ना, because in the reaction medium H2SO4 will be converting I minus into I2. Clear now? So that's why instead of H2SO4 we are adding H2PO4, which is not that much strong oxidizing agent. So that's why in this reaction anyway by default you will get product like Ri, exactly same types. Product will be the almost same pattern, Ri plus K H2PO4 plus H2. Why H2PO4? Because here 3 protons we have and here 1 proton less. There 2 protons are there 1 proton less. Same product you will get, only you have to focus on this RBr and here Ri. So for iodide, for alkyl iodide, always remember Ki in presence of H3PO4 you have to use. So that will give Hi, and that Hi hydroiodic acid will react with ROH and you will get product. Clear now? So this is the idea. Next, this one. So up to last slide we have studied how to convert, how to prepare alkyl chloride, alkyl bromide and alkyl iodide. 3 process done. Next here, instead of HBr we are adding PX5 or PX3. Up to last example we used HX. We used HX in presence of alcohol, means alcohol is reacting with HX and you are getting Rx. Here instead of Hi we are using PX5 or PX3. So what product you will get? This is the source of halide, and this halide it will react, means this X will attack this R means carbon and this will be released. So by default you will get Rx, product will be Rx, correct? And what will be the byproduct in this case? For example, if we study this example, ethyl alcohol in presence of PCl5 we will get ethyl chloride, and what will be the byproduct? We will get POCl3 and H2O. This will be our byproduct. Now question is how we are getting this, right? From this reaction, from this, how we are getting this product? What is the mechanism? What are the steps? So let's see. If we have, just see this mechanism. I'll not discuss in. Let's see that entire mechanism. It will be easier. Let's consider ROH. Okay, and here we have P, X, 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 and X. Correct. Next, this ROH, oxygen is having lone pair, correct? Oxygen is having lone pair. So basically it will attack this phosphorus. Phosphorus is having empty d orbital. Remember, empty d orbital. So X minus will be released. So that's mean from this you will get ROH plus bond P, X. How many X here we will get? 4 plus X minus, because X minus is released here, correct? Next step, this X minus will attack this R and this bond will be broken. So what you will get? R bond, I think it is visible, right? Yes. Rx plus OH bond P X X X X, correct? Next step, so this lone pair will be making pi bond and X minus will be released. So from this we will get OH plus double bond P X X X and X minus will be there, and this X minus will take this proton, right, H plus. So that's why you will get, from this you will get O double bond P X X X and H and X मिलके बना देगा HX. So now just check, if you check this mechanism, so here first we are getting HX, we are getting POX3 means POCl3, in this case POCl3, right, and we are getting HX, we are getting HX, right? HX will also will be the byproduct, yes or no? HX also will be the byproduct, it should be HX, correct? HX also will be the byproduct. So this is the case. Next, exactly same mechanism we will follow in this case, Durgen's method. Instead of PCl5 or PCl3, we are going to use SOCl2, which is thionyl chloride in presence of base pyridine. Exactly almost same type of mechanism. Let's see this mechanism. So let's make a border line. Okay, so what will be the mechanism? From ROH, from ROH we are going to get Cl is there, so we will get RCl. From ROH we will get RCl. SOCl2 is a source of Cl, correct? What will be the mechanism? Can you guess this mechanism? Let's see. ROH and we have SOCl2, means H double bond O, Cl and Cl. Like that PCl5 case, oxygen, okay, it will attack this and Cl minus will be released, correct? So next step, ROH plus bond H double bond O, Cl plus Cl minus, correct? Next step, this Cl minus will attack this and it will go there. And see, these mechanisms are not involved in carbocation formation. There is no carbocation formation. All these are SN2. They are following SN2 process. Direct substitution. There is no intermediate like carbocation. Direct substitution, substituted product we are getting. So it will attack this R, and what product will get? RCl. RCl, alkyl chloride plus OH bond H double bond O and here Cl, right? Next step, this lone pair, this oxygen is having lone pair, right? It will follow, it will go and Cl minus will be released. So that's mean OH plus double bond H double bond O plus Cl minus. Now this Cl minus will take this proton, so you will get O double bond H double bond O plus HCl, correct? So what will be our byproduct in this case? What will be the byproduct? SO2, HCl. So here HCl, we have HCl, and this is our main product, RCl, correct? Okay, and in this case, see, SO2 is gas, HCl is also gas. That's mean using this reaction, this Durgen's reaction, we are getting pure alkyl chloride. Pure alkyl chloride means if you do this reaction, means in the reaction vessel only product you have. SO2 and HCl will be gaseous form, so they will leave that container. So only pure product you will get. This is that's why this reaction is very important, correct? Now we have just this is one example, so that finally just OH we have, replace this OH with Cl, so you will get product, and SO2 and HCl will be the byproduct. Now the question is, using this process SOCl2, we are getting RCl. Now you can ask me, sir, we are forming or we are preparing alkyl chloride, then how I'll prepare alkyl bromide and alkyl iodide, right? Our target is to prepare RX. X can be fluorine, chlorine, bromine, iodine. Already I said that RF bond, that is that is very difficult. That is not conventional way to prepare using this method, especially in case of fluorine. But chlorine, bromine, iodine we can follow, right? We have a lot of process. Chlorine already I studied, but using this process, can we prepare RBr and RI? Can we prepare? Just think, can we prepare those two things? If you instead of SOCl2, means you are preparing alkyl chloride. If you use SOBr2, then you will get RBr, right? Correct? But the problem is SOBr2, it is unstable. Unstable means if this reactant is not stable, how can you perform this experiment? So no, you cannot get RBr in this case, correct? Now if you consider SOI2, actually this compound does not exist. This compound does not exist. So there is no chance of carrying out chemical reactions. So that's why using Darjan's method only we can prepare alkyl chloride. No alkyl bromide, no alkyl iodide. Done? Now this one. So till now what we have studied, from alcohol ROH, how we can prepare RX using various methods, right? Next, from hydrocarbon, if we have a hydrocarbon like methane, ethane, propane, butane, from this hydrocarbon, how can you prepare haloalkane? So famous technique is this chlorine under UV light. Chlorination, bromination, iodination, right? Chlorination, bromination, iodination, this process means these techniques we are going to learn. Now, whenever we have light, always remember, in chemistry, whenever this UV light is given, somewhat you have to assume that some radical rearrangement or radical reaction is happening. Radical steps, radical compound is forming there, or you can consider radical process. Okay, radical halogenation. This radical word will be there if UV light, this type of light word is there. Okay, so that will follow that radical mechanism. So now CH4, if Cl2 is present and under UV light, what product you will get? You will tell, sir, hydrogen is there, chlorine is there. So chlorine will replace this hydrogen and we will get alkyl chloride, right? We will get alkyl chloride, means methyl chloride in this case. Reaction is done, so we will get this product, right? But the point is, chlorine is actually, it is under UV light, it is producing chlorine radical, right? So that chlorine radical means CH4 plus Cl dot. So what we are getting? CH3 dot plus HCl, correct? Now see the steps. Now what we are going to discuss, what we are discussing, we are trying to predict product. If you tell, sir, only CH2 cell will be formed, let's see the mechanism, then we can confirm whether only CH3 cell will be formed or something else. Just check CH3, methyl radical and HCl. You can say, sir, why you are doing like this? Why we cannot write in this way? You know, CH3Cl plus H dot. Okay. CH3Cl plus CH3Cl plus H dot. Why we cannot write this, right? just see, here we have CH4 and chlorine radical. We are writing CH3 radical plus HCl. Why we can't write methyl halide plus H dot? The reason is that hydrogen radical is not that much stable. This is not stable, but methyl radical, it is stable. Okay, so that process of this thing we will ignore, we will follow that one. Next, this CH3 radical we have, correct? This CH3 radical, and there already chlorine radical we have. So these two things will combine and you will get CH3Cl. So CH3Cl will be formed. There is no doubt in that. Methyl halide will be formed. Now the problem is, here we have another 3 radical, right? And sorry, another 3 hydrogens. So all hydrogens will be replaced one by one. CH2, Cl2. Hydrogen will be replaced by chlorine following the same method. From this also CH3Cl3 and from this CCl4. Now just see, here we will not get only one product, we will get multiple product. We will get multiple product like CH3Cl, CH2Cl2, CHCl3, CCl4. Multiple product we will get here. Monochlorination, dichlorination, trichlorination, tetrachlorination. So is it a good method? No, that's why it is not a good method. So multiple product, multiple substance we are going to get. So here we have example. Just check. Not only multiple products, here only one carbon we have. Here we have multiple carbons. So many hydrogens we have. So just imagine how many types of product we will get. So here just check how many types of hydrogen we have. Okay, this is one type. Let's take another color. So this is one type hydrogen, this is another type. This is one type, this is second type. Now this CH2, it is similar to this right side CH2, and this CH3, it is similar to that CH3. Just take, this is mirror image, right? So that's only two types of hydrogen we have. So we will get at least 2 type of product. At least 2 type of product. So one chlorine will replace this hydrogen, another chlorine can replace this hydrogen. Just check this one, correct? So at least we will get these 2 product. This is minimum. Now if it replace this second hydrogen also, one more product you are getting. Another hydrogen means from here only we are getting 3 products. From there you are getting 3 products. So many products you can get, right? So only if I ask you how many types of monochlorinated product, listen this question. अच्छे से सुना ये question है, ये बहुत ही ज़्यादा important है. Question is given like this. In the question I am saying, how many monochlorinated product you will get? What will be the answer? 2. Answer will be 2. Because I said monochlorinated. So only 2 will be the answer. If I say dichlorinated, trichlorinated, then answer will be different. But most of the cases in the question they will ask monochlorinated, right? Monochlorinated product. So here answer will be 2. Acha, next. This is chlorination. If I consider iodination, like chlorine in presence of UV light I said. Now if I say let's use iodine, methane and iodine. So what product you will get? So in that case, we have to remove this part. I hope you have written all of this. Always you should write. You have to make your own class note. Okay. So just check. In this case, methane, if methane is reacting with iodine, so we can expect the CH3I and HI will be the product, right? This will be our reactant and this will be our product, correct? But the problem is, if you carry out this reaction, this HI is strong reducing agent. Strong reducing agent. So that's mean it will reduce this CH3I and this HI will convert this CH3I into CH4. listen carefully. If we add CH4 with iodine, means if we carry out this reaction, methane and iodine, product we will get CH3 and HI, product we will get. Point is, after forming this product, they will react together. ये product आपस में react करने लग जाएगा. This HI and CH3I, they will react. The reason is HI is strong reducing agent and it will reduce CH3I into CH4. That means this reaction is not irreversible. It will be reversible reaction. It will be reversible reaction. Correct? So this reactant and product will be in equilibrium. Then you can ask me, sir, then how to solve this problem? This reactant and we are getting this product, and we know the problem. Problem is this product, again they are reacting with themselves and reactants are being generated. So somehow if we remove this HI from the reaction medium, or somehow if we destroy this HI from that reaction medium, then this reaction will be irreversible, right? We will get methyl halide product, correct? Somehow if we destroy this HI, we will get proper reaction, irreversible reaction, and lot of product we can get. Question is how we will destroy this HI. Just now I said HI is strong reducing agent, so that's mean in the reaction medium you have to add strong oxidizing agent. So if you add strong oxidizing agent in the medium, then that strong oxidizing agent will react with HI and it will destroy that. Basically that strong oxidizing agent will destroy this HI. Now what are the examples? Just now we studied that, strong oxidizing means that iodic acid, like this we have to consider HiO3, HiO4, HNO3, HgO. These are the examples of strong oxidizing agent. So in presence of them, if we carry out this reaction, we will get this reaction. So here this HI will be destroyed with time because all these oxidizing agents are present. This is iodic acid, like HNO3 is nitric acid, HiO3 is iodic acid. This will be periodic acid. This is nitric acid and this is HgO. Can you tell me what is its name? Mercurous acid or mercuric acid? Which one? What will be its name? Here mercury is in +2 form. +2 means eke will be coming, right? So that's why mercuric oxide. The name of this compound is mercuric oxide. Okay, so here HI will be removed. So basically this reaction will become irreversible, means you are getting CH3I. Or you can consider in this way also, if HI is moving out according to Le-Chatelier's principle. Remember Le-Chatelier's principle, you are removing product, so this reactant, more reactants will be converted to product, right? Le-Chatelier's principle, remember, if you remove product, one of the product, so reaction will try to balance that. Reaction will try to generate more product because reaction does not want to lose HI, and you are removing HI means this more reaction you will get, more product you will get. So you will get a lot of CH3I, correct? So this is very interesting thing. Now chlorination done, iodination done. What about bromination? In case of bromination, this is very, very important molecule, N-bromosuccinimide. What is that? N-bromosuccinimide. So one beautiful structure we have here, N, beer, and here double bond O, here double bond O. N-bromosuccinimide, name of this compound. Next here, N-beer bond we have, right? So in presence of light, actually this bond will break and bromine radical you will get, bromine radical. So example we have here. Mainly this is useful in case of allylic or benzylic, okay? Allylic or benzylic system. So PHCC means actually from toluene, this is toluene, right? And here if we add NBS, only this, at benzylic position. So here hydrogen will be replaced by bromine. So what product you will get? So you will get CH3, CH2, Br, CH2, Br. So and here this sentence is very important, because here what we are saying, allylic and benzylic compounds, they are more reactive than saturated compounds in radical catalyzed halogenation reaction. So whenever we have allylic system and benzylic system, because they undergo resonance, that resonating structures are possible, means their radical can be stabilized through resonance or through canonical forms, different types of canonical forms, right? So they are much more reactive. So just this is the idea, right? In presence of NBS, you can get alkyl, means that halide compound, right? This is one example. Acha, next, here we have isopentane. So one interesting question we have, isopentane, they are asking, write all the possible structural isomer expected to be formed on free radical monochlorination. So monochlorinated product you have to consider, and they are saying क्या बोला है, radical method follow करना है, तो UV वाला, right? Isopentane, first isopentane का structure क्या है? Last class में मैंने discuss किया था ये वाला CH3 CH CH3. Okay, this is the, whenever I say iso, this will be our basic structure. Next, total how many carbons? 1 2 3, already 3 carbons I have written, then CH2 CH3, correct? This is the structure isopentane. Now first check how many types of hydrogens we have. How many types of hydrogen? Let's try. This is one type, this is two types, this is three types, and these two are similar, right? 4. So this is 4 and this is also 4. Total 4 types of hydrogens we have. And in the question they are saying monochlorinated, means you have to replace hydrogen with chlorine. So that's mean if 4 hydrogens we have, we will get 4 different product, right? 4 different monochlorinated product. So here we have these 4 structures. All I have written numbers, right? So right side 1 chlorine, then second carbon another chlorine, next third carbon another chlorine, and last fourth one another chlorine. Only instead of replace one hydrogen with chlorine, that is the goal. Clear now? Next, this one, addition of HX. Reaction is electrophilic. See, already this Markovnikov and Anti-Markovnikov already you have studied in class 11th. Again we are going to discuss the same thing. Let's see Markovnikov rules. What it says, पूरा इधर उधर हो गया slide, बताओ. So here, actually here X, right? X will be there. So this is the Markovnikov rules. What it says, so here remember one thing, in case of Markovnikov rules, one trick is there. How we will remember? Markovnikov rule means rich gets richer. Means if carbon is having more hydrogen, if carbon is having maximum number of hydrogen, after reaction it will get some more additional hydrogen. Means here I'm giving one example, then with respect to this example, this is symmetrical, so we will not understand in that way. Just check this one, RCH double bond CH2, correct? Now if we add HX, then how this addition will be happening? So this hydrogen will go towards this carbon, correct? So what product you will get here? CH, and here positive charge will be generated and you will get CH3. Now just check, here CH2 was there, now CH3. That's why I said rich gets richer as per Markovnikov's rule. So this is the trick. So now this one we have an X minus, it will react this, it will attack this carbon or carbocation, and you will get, so this is the product, right? So same thing we are getting. So this is the mechanism of Markovnikov's rule, correct? Easy, very easy. Only if symmetrical alkene, if symmetrical alkene we have, then it is easy, just no problem. If you add X here, hydrogen there, or opposite, both the cases you will get the same product. But if it is unsymmetrical like this, then you have to think, carbon having more number of hydrogens, that carbon will get hydrogen from HX, correct? Or X will attack to the carbon having less number of hydrogen. X will attack to the carbon which is having less number of hydrogen. So this is the way. So in this X, it will attack this and hydrogen will attack that. Simple way, right? Now Markovnikov rule we have understood, very easy. Then what about Anti-Markovnikov's product? So here peroxide comes into the picture. Peroxide is coming into this picture. What is this peroxide? Peroxide means you can consider H2O2, hydrogen peroxide, or ROOR, means RO2R, R2O2. In simple way, R2O2. This is the general form. In presence of peroxide, remember, in presence of peroxide and HBr, both are mandatory. HBr in presence of peroxide, then only you will get Anti-Markovnikov product. What I said, HBr in presence of peroxide, only in this case, you will get Anti-Markovnikov product. Anti-Markovnikov means their rich gets richer. I said na, normal Markovnikov rule. Here opposite, poor will get richer. So that's mean here see only one hydrogen we have, and here two. So basically Br will attack this and hydrogen will attack this. So here X will attack to the carbon which is having more number of hydrogen, correct? X will attack to the carbon which is having more number of hydrogen. This case, as per Markovnikov's rule, there X will attack to the carbon which is having less number of hydrogen. Here X will attack to the carbon which is having more number of hydrogen. Only that thing. Again I am repeating the same sentence. This Anti-Markovnikov products you will observe only if HBr and peroxides are present, correct? Now you will ask, sir, why, how we are getting this product? How we are getting this product? Already see Markovnikov products, already I discussed, there is no problem in that. But Anti-Markovnikov products, how we are getting that product? First let's write, if we have R, CH double bond CH2, so if it is only HBr, then what product will get? R bond CH and here X and here CH2 hydrogen. So this is our normal product. Now Anti-Markovnikov, what it is saying, this is our reactant and what we are adding, HBr in presence of peroxide, means ROOR. And what product we are getting? RCH, hydrogen here and there CH2X. The opposite, right? So now already Markovnikov, that reaction mechanism we studied. Anti-Markovnikov, what is the mechanism? You have to just, you must have that basic idea. What is the mechanism behind this? So R, CH, first example, ROOR. Now always remember this RR means it can be hydrogen, it can be any alkyl group. And this R means it can be the same R or different R, anything. There is no relation. There is no relation. Or there means it can be anything. It can be anything. So this one, first this peroxide will break and you will get RO dot, radical. So whenever we have peroxide, Anti-Markovnikov rule, then radical mechanism will be followed. So RO dot we are getting. Next step, R bond CH double bond CH2. So basically this thing can we write in this way, R bond CH radical bond CH2 radical, like this, correct? Now you tell me this RO dot, right, it will attack to which one? This RO dot, it will attack directly this one or something else. See, in the medium HBr we have, right? So this will react with HBr and we will get ROH plus Br dot, correct? Now this Br dot will attack this, Br dot will attack this alkene system. Now the question is where it will attack? Where it will attack? This Br dot will attack this carbon or this carbon? Which one? So to answer this question, you have to know the product. First one, RCH Br bond CH2 dot. This is one thing, means this first one we will get this product, and if you consider second thing, what product will you get? R bond CH dot bond CH2 Br. This is second one. So one or two, which one is more stable? Can you say? Yes, sir, this is first degree radical, this is second degree, 2 degree radical. Then 2 degree, we already know 2 degree radical is more stable than 1 degree. Means what is the stability order of radical? 3 degree greater than 2 degree greater than 1 degree. Simple way, right? So 2 degree will be more stable than 1 degree. So that's why this first step will not be followed. We will get second step, right? So that's mean if Br attacks this CH2 dot, CH2 radical, then we will get CH radical bond CH2 Br, correct? Clear na? Now in the reaction medium already HBr is present, right? So this HBr, here we have hydrogen, again it will produce, hydrogen radical and Br radical, and this hydrogen will attach to this and you will get RCH bond H bond CH2 Br. Now just check, this is our final product, which is exactly opposite to this. So here Br we have, right? So it is opposite to this, correct? So through this radical mechanism, we are getting this anti-Markovnikov product. Now you can question me, sir, why you are specifically writing HBr? Why here we are not writing HX? Means HCl. Can we write HCl here? No. This peroxide effect or Kharas effect, there is a proper term called Kharas effect. SCH, Kharas effect. It is observed only in presence of HBr and peroxide. Right? Now peroxide you can vary, H2O2 or something else. Peroxide, this common name, peroxide must be there, but only in presence of HBr. Question is why? Why in case of HF, HCl and HI, we are not observing peroxide effect? Why? Reason is, you have to check this radical mechanism. Just look at carefully. So here first step, this is our vital first step, where bromine radical is attacking this alkene system. This is the first step. Second step, after this radical formation, this H plus will attack, means H radical, hydrogen radical will attack this, and you will get Br radical, right? So this is our second step, first step, and this is second step. Now if you compare first step and second step, this is first step and this is second step. If you compare HF, HCl, HBr and HI, if I compare these four things, always remember radical mechanism means if reactions are exothermic, it is self-sustaining process. If reaction is exothermic, means heat producing, then it will be self-sustaining process. That reaction will be going on. If endothermic, if it is endothermic process, no. So just check for HF, first step is exo, second step is endo. So endo process is involved, so that's why it will not show. For HCl, the same story, exo, endo. That's why this also do not show Kharas effect. These two are not showing Kharas effect. HBr, first step is endo, second step is exo. Again, it will not show. Only in case of HBr, first step is exo, second step is also exo. Both are exo. So that's why only exothermic means that radical mechanism process, that is self-sustaining process. So that's why only HBr can show Kharas effect. Only HBr can show Kharas effect. Okay, Anti-Markovnikov rule. Clear na? So here so many things we have discussed. Okay. Next part. So here we have halogen exchange. Up to third process we are done. So now halogen exchange. So here we have two reactions, Finkelstein reaction and Swarts reaction. So in Finkelstein reaction, so here basically see dry acetone is there. Mechanism is very simple, very simple. This I minus, this is ionic compound, right? It will attack and Br minus will go. And here what will be the product? Product will be Ri plus NaBr. Now see this NaBr, this is ionic compound, right? And dry acetone, it is not that much polar molecule. Polarity is not that much. So that's why in the reaction medium, this NaBr will be settling down. So that's mean it is not that much soluble in acetone. So that's why we use acetone here. Just iodide we are using, and it will replace this bromine. And always remember, Finkelstein reaction means it is this name is connected to this Ri, alkyl iodide. To produce that, we are using this Finkelstein reaction. Okay, so here we have one example. Okay, CH3I. To prepare alkyl iodide, we are using this Finkelstein reaction. This is name reaction, specific reaction. Now Swarts reaction. So here basically we are using inorganic fluoride. This term is very important. Inorganic fluoride. Inorganic fluoride. So inorganic fluoride means metal fluoride. Metal fluoride. What are the sources? SbF3, AgF, then Ag2F2, COF2, etc. Okay. All see this 3, 2, 2. This will be going down, right? So just clear this. It is not proper format. So SbF3, AgF, Ag2F2, COF2, right? So this is the case, like this. So here basically this F minus will attack this, and this chlorine will be removed. So you will get this product. Again AgF, we are getting this product. So this is also name reaction, Swarts reaction, very specific reaction, and we may use, there is a lot of question, there are a lot of questions based on this name reaction. Achha, here we have one question. What will be the product here? Just check. We have HBr and this. There is no peroxide, so that's mean it is Markovnikov rule. It will follow Markovnikov rule. So Br, this hydrogen rich gets richer here, so hydrogen will be here and bromine will be there. Correct? Clear now? So second case, what will be the product? Here peroxide is there and HCl is there, and we know HCl does not. So first one, Markovnikov product it will show. Second one, Markovnikov or anti-Markovnikov. HCl does not show peroxide effect or Kharas effect. So here also you will get Markovnikov product. Third case, HBr and peroxide both are there. So here anti-Markovnikov product you will get. So that's mean Br will be attached here and this one this. Correct? And here hydrogen will be here, chlorine will be there. Now just check the product. Okay, so the same product we are getting. So reactions will be there. If it is following Markovnikov rule or anti-Markovnikov rule, we have to decide based on the reagent, right? Okay, so already up to here all haloalkanes, so many process we have studied, alcohols, then using that halogenation process, so many things, inorganic fluoride, so many things we have studied. So just you need to practice PYQs. If you have, just practice that. Based on this, I think you can solve all type of problems. Okay, so now here we have our own Telegram channel. Join this channel, so we will get, you will get a lot of updates lot of updates will be there, so join this channel, it will be helpful for you. And this is our YouTube channel. Subscribe and just get that bell icon is there, just press that, so you will get notifications. So because every day we are conducting live classes, and all the classes full of content, and all are very much useful for your exam. Okay, right? Just if you follow this one, if you just focus whatever we are studying, this is very, we can say it will support you in the maximum level, right? So just subscribe this channel. Thank you very much. So tomorrow, next class, we're going to study how we will prepare aryl halide, right? So that preparation method we are going to study. So I hope this class is you have got a lot of benefits from that. So next class में मिलते हैं.